Good afternoon, everybody. Welcome to a nice afternoon of Chem 170, almost said the wrong class, Chem 170 at Elgin Community College with your host, me, Dr. White. Now, a couple of things I want to talk about. And the first thing is tomorrow, Thursday, is Yom Kippur, one of the holiest holidays for Jewish people. And what that means is from tonight, sundown, till tomorrow, sundown, I will not be turning on my computer because of the high holiday. And therefore, I won't check my email until tomorrow, sundown. So normally I check it morning and afternoon and night, minimum morning and evening, but I won't tonight after sundown tomorrow. So I just wanted you to be aware of that. Also, I guess the best greeting for tomorrow, Yom Kippur, is may your name be a bit written in the book of life for next year. Or another one is Good Yontif. All right, another thing I want to talk about is test number 1. Does everybody see D2L, Chem 170? Thank you. And I posted this about 11:30 this morning, 11:31. All right, first of all, and you should have gotten this in an email also. On a week from today, the 22nd of September, I will give test number 1 online. The Tuesday before, what you'll do is you'll be downloading a password protected PDF file for test number 1 from the assignment area of D2L, just like you've been doing labs. But this will be test number 1. That will be available Tuesday afternoon on the 21st. Wow, 9/21/21. Wow. But anyways, next Wednesday at 3:30, give or take a few minutes. In other words, after the lab, I will send out an email with the password for test number 1. And you will have until Thursday morning, 10 a.m. to finish test number 1 and upload your answers as a single PDF file to the assignment area D2L. It should take you about 40 minutes more face-to-face. Test number 1, most students, assuming you studied and done the practice problems, hint, big hint. But if you need up to an hour or so, go right ahead. Test number 1 has 10 pages, 14 problems. Some of the problems are multiple part. I have never and never will give a multiple choice question on a test in Chem 170. It covers hydrocarbons, alkanes, cycloalkanes, alkenes, alkynes, and aromatic compounds. This test, as all my tests, will not be open notes. You shouldn't look at your notes. And obviously you shouldn't go on the internet or ask anybody else to give you help, because that's cheating. And I will do what's in my syllabus if I catch a student cheating. And I have things I've learned online how to put things to find out as students do. Now, here's the point breakdown for test number 1. 13 points are general knowledge. What would be general knowledge? I don't know. I think everybody taking organic should know how many bonds to carbon. And then there's nomenclature questions, 45 points. What's the nomenclature question? There are 2 types. One is, here's the structure, give the IUPAC name. The other is, here's the name, either common or IUPAC, draw the structure. And finally, 47 points are reactions. And what do I mean by a reaction problem? All but one will be give the product or products, or give the organic product or products for this reaction. The one that won't be like that, there'll be one what I call synthesis problem, which is give the starting materials. And if you notice, it adds up to 105. And that means there's five, yes, five bonus points. Now, I don't do what other teachers do and say, the last problem I'm going to make super hard, and that's going to be the bonus question. No, I just have the whole test add up to 105. You pick whichever question or questions you want to call bonus, but there's 5 bonus points. And I found doing that helps students do better on my test and also makes for you for a happier student, which is a good thing. Now, I've attached files, which you've also seen in the labs, how to scan and upload a test, or as you've done for a lab in 170. Now, next Monday, I will review the material for test number 1 in our Zoom meeting. We'll have our regular Zoom meeting on Wednesday. We'll have lecture and lab, and then when we finish, I will send out the password. You've got the rest of the day and the Thursday morning to finish test number 1 and upload it. And one of the things next Monday, I will do, like I just said, my world famous review for the next test, in this case, test number 1. And students have told me it helps them do better on my test, which is why I do that. All right. Another thing I should mention, I don't know if I was going to do it today, but I decided, let's do it on Monday. On Monday, I will also go through the aromatic compounds problem set. On Monday, I will go through the aromatic problem set. Any questions about test number 1? Speakers on. So when I first started doing Zoom, I forget I have 2 big, they're about this big amplified speakers. I forget to turn it on, and nobody can, what are you saying? I can't hear you. I've learned to check. All right, couple things about my test. 1, do the practice problems. After test 1, you will find out why I call them practice problems. And for those of you who know, Monty Python and the Flying Circus is wink, wink, hint, hint, say no more. You should understand that. The other thing I should tell you about my test, and it's also true about my final, every question on my test, everyone, the concept behind that question, I discussed at least twice in our Zoom meeting, usually more than twice. So that's a promise I always make to myself, to make sure every question I've discussed the concept in our Zoom meeting, in other words, in a lecture, at least twice. Usually it's a lot more. Any questions? All right, don't forget to hand in the lab today if you haven't. Also, don't forget, and 2 of you haven't, send in your upload to the assignment area D2L, your signature sheet. Because if you don't have it, I'll give you 0 points for test 1. That's in my syllabus. All right, let's get back to alcohols. I was talking about alcohols, and alcohols, remember, carb with hydroxyl group on it, OH, hydroxyl group, and this is an alcohol. And we already went through the nomenclature, how to name them, and how do you make one? Well, this is the only reaction the whole semester that I'll have on 2 tests. Both test number 1, we learned this, and now you're going to learn it again or review it again for it can be on test number 2. And that is, if you take a double bond, react it with acid and water, you'll get an alcohol, and I should have had here, it follows Markovnikov's rule. So let's try a couple. And that's your turn. Have fun. What would be the organic product or products for the following? Also, this is a good review for test one, because I can put this reaction on test one, because we discussed it there too. And don't forget, tonight, since luckily it's before sundown, I will have my office hours from 5 to 6:15. If you have any questions whatsoever about anything that I can help you with, stop by. It's on Zoom, so you don't have to get in your car and come to ECC. Yay. And when you're done, give me a thumbs up. Thank you, Joe. Thank you, Megan. Oh, I think everybody's done. So I better get to work. What do you see that's different? When you look at a molecule, organic molecule, you should look for what's not a carbon-carbon single bond or carbon or hydrogen atoms. And here we have a double bond. And if we're reacting with acid, H+, that's a catalyst. And water, remember water is H, OH. You break the pi bond, remember double bond is one pi bond, one sigma bond. And pi bonds you can break like, oh, my snap is gone. You can break like that. You'll see that later today. And each carbon of the double bond gets something. One carbon gets H, the other gets the OH hydroxyl group from water. And how do you know which? Follows Markovnikov's rule. And what's Markovnikov's rule? The carbon with the most hydrogens in the double bond gets the hydrogen, the other carbon gets the hydroxyl group. And this has two, this has one, just because I like to remember it. When I learned it, my instructor also taught us the rich get richer and the poor get poorer. Now, do you break carbon-carbon single bonds? No. So I start out with 4 across plus some methyl here. Here are my 2 carbons of the double bond. This has 2, so the hydrogen will go there. The hydroxyl group will go on this carbon. I know there are 4 bonds to carbon. That's one of your big friends a week from today. And I can put in my hydrogens. And remember, it's your solemn responsibility. If I make a mistake, which I don't think I did, correct me, please. And that's the answer. Oh, let's try one more. And there's one more for you to have fun with. If I say fun enough times, you might believe me, and it is. Thank you, Megan. Thank you, Emily. So now got you all trained for thumbs up. And unfortunately, that's a problem with Zoom and also with the fact that we're not face-to-face. Because when we're face-to-face, I can just look at the class. And I usually say, when you're done, look up and smile. You don't have to, but most of the class do. All right, I think everybody's done. I better get to work. If we look at this molecule, what's different? A double bond. And here are my 2 carbons double bond. What am I reacting it with? And why I look at that, that's the only place something's going to happen at the functional group. And now I'm reacting with acid and water. H plus is acid. Remember, water is H and OH. You break the pi bond. Remember, this has one pi bond, one sigma bond. And one carbon gets H, the other gets the hydroxyl group OH, and it follows Markov-Nikov's rule. And rings don't have hydrogen. They do, you just don't show them. And as I keep on telling people, Dr. White and Mother Nature, who's the greatest of all organic chemists, love rings, students don't. Count bonds. This carbon right here has 4 bonds to it. 4 minus 4 is 0. This carbon right here has 1, 2, 3 bonds. 4 minus 3 is 1. And that's how many hydrogens on each of those 2 carbons. And do you break carbon-carbon single bonds? No. So I'm going to have my ring. I'm going to have my 2 methyl groups. And I broke the pi bond. And the hydrogen, Markov-Nikov's rule, goes to the carbon with the most hydrogens. And the hydroxyl group goes to the other. Excuse me. And you could write it this way. You could also write it this way. For this class, there's no difference. And that's how you do it. All right, let's move on. Now, there are other ways of making alcohols, but we'll cover those when we do other functional groups. And now let's get to the fun part, reactions of alcohols. And before we do this one, could I have everybody's attention? Could everybody please, let me do something first, which I don't think I did. No, I did. All right, everybody, take a deep breath. Let it out. Take a deep breath. Let it out. Are you all relaxed? The next reaction is one of the more challenging ones you'll learn this semester. Take a deep breath, relax, let it out. And at first, students have trouble with this, but with a little practice, you'll get it. So if it's a little, what's going on? I don't understand. Just relax, you'll get it if you practice, and I have practice problems for it. All right, what's this reaction? Well, if you take an alcohol, and notice what I have here, what's an alcohol? Carbon with a hydroxyl group. Now, if you take an alcohol, and on the adjacent carbon right next door, there's a hydrogen, and you react it with sulfuric acid, H2SO4, this means heat. It looks like the top of a flame on a Bunsen burner. And sometimes I will, in this case I did, I don't always, you really got to heat it high, and 180 degrees Celsius is high. You lose water, and between these 2 carbons, you form a double bond. Now you can see Dr. White, being an organic chemist, is discriminatory against inorganic compounds. Yeah, we don't like them. And you could have put here H2O. You don't need this, but this is called dehydration of an alcohol to make an alkene a double bond. And I will show you an important problem that existed that another great Russian scientist solved. And this reaction follows Zaitsev's rule. And that great Russian organic chemist is Zaitsev, or Dr. Zaitsev. And do not write down what Zaitsev's rule is. I'll explain why in a second. The major product in an intramolecular alcohol dehydration reaction is the alkene that has the greater number of alkyl groups attached to the carbon atoms of double bond. What? What is that? Well, let's learn what this means. And this was a very important I don't know if you call it discovery or elucidation, clarification. All right, let's look at a molecule. If I react it with sulfuric acid and heat, I could also put the temperature down. I'm being lazy right before Yom Kippur, which I shouldn't be. But anyways, what is this? Well, look for what's different. Oxygen with a hydrogen, alcohol. And as soon as I see sulfuric acid, H2SO4, and heat, I know I need a carbon adjacent to that with a hydrogen. And what happens is between these two carbons, you lose water and you form a double bond, but it follows Zaitsev's rule. And instead of you watching me print out Zaitsev's rule, Zaitsev's name, and getting it wrong, I'll just use Z, just like I did with Markovnikov. Now it's time to go technicolor on you. If you notice, the carbon with the hydroxyl group has two adjacent carbons with hydrogens, A and B. If I lose the hydrogen from A, and the hydroxyl group between this carbon and this carbon, I'll form a double bond. That's the dehydration. Do you break carbon-carbon single bonds? No. And that would be one product, A. Now, let me make some room over here. I could have B if I lose the hydroxyl group here and the hydrogen from B between these two carbons, I'll form a double bond. Do you break carbon-carbon single bonds? No. Now the double bond is between these two carbons. And the way I teach Zaitsev's rule is, which do you get, A or B? In real life, you get most of one and a little of the other. But the way I teach it is you just get one or the other. Again, one or the other. So how do you know which one you get? Zaitsev's rule is count the carbon atoms. Count the carbon atoms directly bonded to the carbons of the double bond. This one has that carbon, and it has only one carbon atom directly bonded to the carbons of the double bond. Now this one, B, has this, this, this. And if I count, that's 3. And Zaitsev's rule is the one that has the most carbon atoms directly bonded to the carbons of the double bond is your product. Therefore, the answer is B. And that's Zaitsev's rule. Now, notice in A, I didn't count these carbons that weren't directly bonded to the double bond carbons, and that's part of Zaitsev's rule. So let's go through this again. I have an alcohol. You're reacting with sulfuric acid and heat. The little triangle here means heat. And what happens is alcohol with a hydroxyl group and adjacent carbon with a hydrogen, you lose water, HOH, and you get a double bond. And if you have a choice between two possibilities, which we do, because here's my hydroxyl group, A has a hydrogen adjacent carbon, and B is an adjacent carbon with a hydrogen. So you can form potentially two different products. If I lose the hydroxyl group and A, I will get this compound. If I lose the hydroxyl group and the hydrogen on B, I'll get this one. And now Zaitsev's rule is you count the number of carbon atoms. This is important. You count the number of carbon atoms directly bonded to the double bond carbons. And if you look at the A, there's only one, the one I have circled. Remember, atom, not the whole alkyl group or all carbons. In B, I have three, which is the greater number, three. Therefore, you don't get this. This is the product you get. Now, one of the things I like to do for Zaitsev's rule is hold off on doing any more examples and ask you to try. And probably next week or after the test, we'll come back to this, because that will give you not this weekend, but next weekend time to try it. And that's Zaitsev's rule. And that reaction is quite challenging. Probably one of the two or three I'll do of all the reactions this semester. We'll come back to it. Let's move on. Now, let's do an easier one. And the easier one is, remember, ROH, alcohol, reacted with an acid, and bad Dr. White, I didn't put here, this can be chlorine, bromine, or iodine. You replace the hydroxyl group OH with the halogen. And this happens on the carbon with the hydroxyl group. So if I take an alcohol, and what you're forming first is, remember how I showed you H plus reacts with OH to make water, and it goes through that, what we call a carbonium ion. But I don't teach mechanisms in a one semester course. I just don't have time. It'd be fun though. So let's practice this. And the question is, what's the organic product or products are the following? Oh, by the way, tonight, no, I can't do it tonight at midnight because it's Yom Kippur, but over the weekend, if you need it, I will be giving lessons on speed structure drawing. No, I won't. All right, what's different? Oh, hydroxyl group. Remember, look for what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, oxygen. That gets my attention real quick, like that quick. Anyways, alcohol, HI, ooh, halogen, hydroiodic acid, HX, where X can be chlorine, bromine, or in this case, it is iodine. And what happens is you replace the hydroxyl group with the halogen on the carbon that the hydroxyl group was attached to, which in this case is this. Do you break carbon-carbon single bonds? No. So I have three across, and this will replace the hydroxyl group with the iodine. That counts as one bond. And I know there are four bonds to carbon, and that's how you do it. It's a lot simpler reaction. Your turn. Give the organic product or products are the following. That's the ugliest looking hydrogen. Let me fix it up. That's better. And when you're done, give me a thumbs up. All right, everybody done? Let's do it. What's different? Ooh, hydroxyl group. What do we have? An alcohol. What are we reacting with? HBr, halogens are X. Remember X, excuse me, can be chlorine, bromine, which it is in this case, or iodine. You rarely use HF because it's a really dangerous chemical to work with. And you replace the hydroxyl group with the halogen on the carbon, the hydroxyl group. To break carbon-carbon single bonds? No. So we have 4 carbons. I better end up with 4 carbons. Which carbon has the hydroxyl group? That one. And it will have now the halogen. And there you go. Oh, let's try one more. And there you go. What would be the organic product or products for the following? Three points each. Everybody done? All right, let's do this. I look at this molecule, what's different, what's not, carbon-carbon double bond or carbon or hydrogen. Ooh, oxygen with a hydrogen. It's an alcohol. And I'm reacting with HCl. Remember, chlorine is the halogens we show by X. And this could be chlorine, which it is, bromine, or iodine. And what happens is you replace the hydroxyl group with the halogen. You also get water, but I'm asking only for the organic products on the carbon that the hydroxyl group is. And this is chemistry instructor's favorite trick on the test. Put a big scary molecule if you don't know what you're looking for. Well, you do, hopefully by now. Do you break carbon-carbon single bonds? No. So everything comes along for the ride. The ring still has its ethyl and methyl group. The carbon with the hydroxyl group, this carbon, will get the halogen, in this case, chlorine. And that's how you do this. All right, let's try one more. And this is a synthesis one. On test 2, unlike test 1, I usually historically put 3 synthesis problems. Not too many? Ooh, guess what? Dr. White got lazy. And on test 2, I put 3 synthesis. So what would be the starting material that you react with HBr to make that molecule? And this is the fun part of organic chemistry. How do you make something? How do you work backwards? Don't forget, I know a couple you've already have, do a thumbs up when you're done. All right, I think everybody's done. All right, now, the question is, how do you do this? Well, you look at the product and look for what's different. What's not carbon, what's not hydrogen. Ooh, a bromine on a carbon, alkyl halide. Reactant, remember, X can be chlorine, bromine, which it is, or iodine. I'm reacting it with HX. And what do you react with that? An alcohol. And the carbon with the hydroxyl group will be the carbon with the halogen. So I can go in reverse. Going from here to here, do you make or break carbon-carbon single bonds in this reaction? No. So I know I have these carbons. The carbon with the halogen will be the carbon with the hydroxyl group. And that's how you do it. All right. That's how you react an alcohol to make a halogen. Now, what I'm going to write down on the whiteboard, do not copy down. What if I wanted to replace this hydroxyl group with a chlorine? But now in this molecule, notice I also have a double bond. Well, if I reacted with HCl, what would happen? Well, I'd get a mess. What do you mean you get a mess? Well, there's 2 reactions. The one you just learned, and because I have a double bond, the other one we've done in the past, I have a double bond react with HX. I'll add across, break the pi bond, and it follows M's rule. So I could get 3 products here where I replace the hydrox group with chlorine, where I react the double bond. What most likely will happen is both will happen. And this is definitely what I don't want, because I wanted to keep the double bond. I didn't want to lose it like I did. So what do you do? Well, it turns out this happens a lot in organic chemistry, where you have what's called competing reactions. In this case, and I don't know who came up with it, reaction of alcohols with thionyl chloride. Thionyl chloride is SOCl2. I'll never ask you what it is. By the way, this is a very challenging, dangerous chemical to work with, but I've worked with it. It's one of those who separate those who will become organic chemists from those who won't. It does scare a lot of people. And if you take an alcohol and react it with thionyl chloride, you replace the hydroxyl group with a chlorine on the carbon, which has the hydroxyl group. Now, thionyl chloride will not react with double bonds. So the reaction before, I would have used this. But now let's take a look at thionyl chloride and how you use it. And if we look at this reaction, the question is, what's the product of products? Well, you look what's different here. Ooh, an oxygen with a hydrogen on a carbon, alcohol. Thionyl chloride, SOCl2. You replace the hydroxyl group with a chlorine. And what carbon has the hydrox group? This one. Do you break carbon-carbon single bonds? No. And that's the product you get. And it's your turn. And by the way, if you can't make out anything I ever write on the board or my whiteboard, always feel free to ask, what the heck did you just write? Or be more polite about it. Give the organic product or products are the following. Aren't you proud of yourself? You're doing organic chemistry and it's not painful. Hopefully it's not. All right, I think everybody's done, so I'm going to get to work. I look at this molecule, what's different? Ooh, oxygen and a hydrogen and a carbon. It's an alcohol. Reacting with thionyl chloride, SOCl2. And what happens? You replace the hydroxyl group, OH, with a chlorine on the carbon that the hydroxyl group is. Do you break carbon-carbon single bonds? No. So I have 4 across and my methyl group. Here's my carbon with the hydroxyl group. This one, it will get the chlorine. And I know there are 4, yes, 4 bonds to carbon, so I can put in the rest of the hydrogens. And a halogen counts as 1 bond to carbon. And that's how you do it. Oh, we got to do another one. And there's another one for you to try. Oops, somebody should have caught me. I forgot a hydrogen there on the isopropyl group. Bad, Dr. White. All right, I think everybody's done. So let's get to work. If I look at this molecule, what's different? What's not? Carbon single bond. What's not? A carbon or hydrogen atom. Oxygen with a hydrogen on it. Alcohol. Thionyl chloride, SOCl2. Replace the hydroxyl group with a chlorine. And everything else stays the same. That's on the carbon with the hydroxyl group. Well, do you break carbon-carbon single bonds? No. So I can immediately write this. And the carbon here with the hydroxy group on the ring will be this carbon with the chlorine. And that's how you do it. By the way, once again, I did the chemistry instructor's favorite trick on a test, put a big, scary molecule, but if you know what to look for, it's not big and scary. Now, we're getting into the good stuff of this semester where you can ask the following question. Why am I learning this stuff? Well, the obvious answer is because you want to get a good grade, so you get into a school or program you need organic chemistry for. But why learn organic chemistry? How many of you have ever heard of artificial sweeteners? They're in a lot of our foods today. Being someone who's been unfortunately overweight most of my life, actually I used to weigh about 60 pounds more, and I took it off, and I'm still taking off. Right now, I'm taking off, finally getting to take off my pandemic weight. But anyways, I used to take artificial sweeteners and buy stuff I don't, and I'll explain why. But what's one of the most popular artificial sweeteners? Splenda. And here we have Splenda in Wikipedia, and it's a very popular artificial sweetener. And the main ingredient in Splenda is a compound called sucralose. And does everybody see the structure of sucralose on the screen right now? Give me a thumbs up if you can see the. All right, thank you. Now, every bend in a line is a carbon. And notice on sucralose, I have a chlorine here, I have a chlorine here, and I have a third chlorine here, Cl, each one on carbons. Now, why is it called sucralose? It's a common name because it comes made from the compound sucrose. And here's sucrose. What is sucrose? Well, you know it as table sugar. That's the white stuff you also call the sugar. And what they do is they take sucrose, which is quite inexpensive, but sweet, and replace 3 of the hydroxyl groups with chlorine to make sucralose, this one, and this one. Now, what they don't tell you is usually companies keep things like that trade secret. I've made molecules which are trade secrets, but one of the 2 reactions I just showed you, reacting an alcohol with HX, or in this case HCl, or reacting an alcohol with SOCl2, thionyl chloride, is how they're making sucralose. So why are you learning this stuff? Well, the reactions I'm teaching you are used to make things in your daily life, such as, I don't know if you use it, but I don't know, sucralose, I think, is about $1 billion product. It's huge, multi-million, if not billion. Now, I'm going to go 1 or 2 minutes into our break, and I'll still give you a 5-minute break. But personal story about artificial sweeteners I like to tell. About 5-6 years ago, I got into making my own kimchi, which I don't anymore, because twice I gave myself food poisoning. I've never done that cooking. I do a lot of cooking, but making kimchi and keeping it too long when I make it, dangerous. Well, the second time I got it bad. I had to go to my doctor to get help. And I asked him, I just read an article in the New York Times. I read a number of newspapers every morning. It's online and it's free, most of them. Well, New York Times, through our school and the other school, you can get a free access or subscription. But anyways, there just been an article about these 2 gastroenterographers, I'm saying it wrong, GI doctors who are also overweight. They were wondering, they're taking artificial sweeteners and they're not losing weight. What's going on? Well, they did something. They looked at the flora, the microbes in their gut, and probiotics, it's called, And I won't tell you, it's sort of yucky how they analyzed it. They also did it with about 15 of their colleagues and friends. And they measured the probiotics or the flora, the microbes in there that was in their gut before they took sweeteners and afterward. They found out about 80% or more of the probiotics, the microbes in there, were killed when you drink or eat something with an artificial sweetener. They tried a couple different brands. I believe Splenda was one of them. And because of that, it made you hungrier. Well, if you're trying to lose weight and you're hungrier, so you're going to eat more, guess what? You're not going to lose weight. Well, about this time when I had the stomach problem, poisoning, which was not fun. But anyways, I asked my doctor, was very good. I belonged to a really good health group, NCH health group. They have some fabulous people in there, my cardiologist. I've also had physical therapy through them. But anyways, I asked him and he said, yeah, I saw that. And plus, when I eat stuff, and I have very sensitive stomach, my doctor, not me. I can eat usually anything, it won't bother, but not when you give yourself food poisoning. But anyways, said, well, even if I chew gum with artificial sweetener, it gets my stomach upset. So I gave it up. So I asked him, should I give it up? He said, that'd be a good idea. And I went back to putting sugar, well, this afternoon, so I don't have my cup of tea to show you, instead of sweetener, which I had been using for years. And I figured, well, I got to watch, I'm going to gain weight. And I didn't using sugar. I now keep an eye on what I eat. But so, moral of the story is stay away from artificial sweeteners. All right, it's a 1:53. Why don't you come back at 1:58, give or take a minute? I'll see you in 5 minutes. I can get up and stretch, and we're going to come back and have our lab for today. See you in 5. Time to start. Everybody back? Let me do one more. One of my hobbies is model railroading. All right, everybody back. It's lab time. If we were face-to-face at ECC, what we would have done today is I would have lectured in a lecture classroom from 1 to 1:50. Then we take a 5 to 10-minute break usually when we're face-to-face. And at 2 o'clock, we'd start the lab. Well, it's time to start. So let's go. Now, these labs, long ago when I inherited Chem 170 and they were awful what they had, I rewrote, and part of the reason I had to rewrite it is when we're face to face, we only have an hour and 50 minutes, which if you look at the standard lab books for one semester organic, most labs are more than an hour and 50 minutes. Some say 2 hours and 10, 2 hours, and I couldn't do that. So I wrote my own. And the philosophy you'll see this semester is, how do I give you a feel for organic chemistry and organic chemicals? Now, one of the problems when we're face-to-face, I mean on Zoom like this, not face-to-face, is you can't smell things, but you can look at things. But part of the minor experience you won't have is smelling things, but I think you can get over that. All right. Today's lab deals with alkanes and alkenes. And let's take a look at it. You can download it from the assignment area of Blackboard, wrong school, of D2L. And if we were in the lab, remember all hydrocarbons are flammable. And in the organic lab, you never light any matches, lighters, or Bunsen burners, never. And we also follow when we're face-to-face disposing of organic waste and waste bottles not down the sink. All right, first part, hydrocarbons. How do they smell? Well, if we had been face-to-face, we have set up samples for you to try. Dr. Daly, who's the lab manager, and he also teaches 2-semester organic, did a wonderful job. I haven't seen him in almost a year and a half face-to-face because I don't have to go to ECC because I teach on Zoom. We have talked on Zoom, but not face-to-face. But anyways, he did a great job, and he cut up these little pieces of paper towel. And when you smell something, put a few drops on the paper towel, stick it under your nose, or go like this and smell it. And what I ask students to do is write down what they smell, their observation. Now, interesting thing about odors, and later in the semester, one of the most difficult industrial problems I had to solve dealt with odors, and there were about $60 million a year on the line. If I didn't solve it, talk about pressure, but I'll talk about that later. So what you would be doing is smelling hexane, octane. Now notice I don't have octene, which one. Sometimes we have one octene. Let's, for this lab, make that one octene. Sometimes in the lab, we have two octene, and then limonene, and then naphthalene. Now, notice in red, what I'd like you to do for this table only, draw the structures underneath the name. Again, for this table only, draw the structures underneath the name. You should have enough room for hexane, octane, one octene, limonene, naphthalene. I don't know why part of this table got put on the next page. I apologize for that. And that would be the first part. Now, the second part, let's talk about reactions of double bonds. And we've talked about this in the lecture, but let's talk about it in lab. If you have any double bond, that means R and R prime can be carbons, can be cis or trans, and react it with a halogen, you break the pi bond and each carbon gets a halogen. And if I were to show that to you on the whiteboard, now, alkenes, double bonds, are usually clear or slight yellow color. Unfortunately, you don't know the different scales for color like I do that we use in industry. So I would have given you a number now. It's a Gardner 2 or less. But anyways, in organic chemistry, before we had a lot of the electronic instrumentation we now have, how do you know if you had a double bond in a molecule? Well, you did the classic visual test by reacting with bromine. And bromine, and say something like carbon tetrachloride or chloroform, this is a red brown color solution depending on the concentration of the bromine in the solvent. And when you react it with a double bond, the dibromide is also clear or colorless. So when you add bromine to a molecule, if the solution stays clear or just very slightly yellow, you know you have a double bond. If it turns a red or reddish brown, you don't have a double bond. And that's what you're going to be testing here. What you would do if we were face to face, whatever hydrocarbon, you put about 5 to 10 drops in a small clean test tube, add a few drops of the bromine solution, and then wait a couple minutes and observe. Now, at COD, when we did this lab one semester, and bromine in a solvent is a very heavy solution. And students have problems with that. And an eyedropper, plus the heat of your body, your hand, also affects the boiling point of the bromine in there. And what happened was, I can still picture it happened twice. In a lab, students were taking bromine, and students twice got bromine on the back of their neck from another student, not on purpose. I had to take care of it immediately and then send them at back time. We actually still had a nurse at COD. After that, I said, nope, I'm going to do it myself for ECC and COD when we do that. It's safer because I know how to handle bromine. But now, through the miracle of YouTube, can everybody see the YouTube alkene on your screen? Thank you. And notice in the alkane, they're adding bromine. And see how it's getting brown? That's because the bromine is not reacting. What do you call that? Reddish brown. My sister's always, you don't know your colors that well. I know red, green, and blue. Now look at the double bond. See how it stays clear? That's how quick the bromine is reacting with the double bond. And that's how you use this test to determine it. And I would show you this for different samples. Now, in the lab, you'd watch me do this. When I did cyclohexane, it would be red-brown. When I add the bromine to 1-hexene, it would stay clear. And let's just use 1-octene here. If I had 2, it would be the same thing. It would stay clear. And limonene would also stay clear, double bond present. Now, to make this lab interesting, I have 2 unknowns, cleverly named unknown A and B. When you add bromine to unknown A, it stays clear, and unknown B, when you add bromine solution to it, goes reddish brown. And later on, you'll see some questions which you'll have to answer, and using your knowledge of this test, what clear and red-brown means. All right, let's move to the last section. And that's, again, another way of identifying a double bond in a molecule. Now, this is a reaction I didn't show you in the class, but let's go to my whiteboard. If I have a double bond and I react it with potassium permanganate, KMnO4 solution, usually that's in water with a little acid, and it's called acidic potassium permanganate. This is purple. And you know this is clear or yellow, really slightly yellow, a Gardner 2 or less. If this reacts, what happens is you break the pi bond, and I'm not going to go through the mechanism. You put a hydroxyl group, and this, by the way, anything I do in lab will never be on a test in the lecture. My lecture tests only have material that's in a lecture. This is called an oxidation. If this is oxidized, this is reduced. And what you form mainly is manganese dioxide. And the best way I found to describe this is a muddy brown color. And if you take a molecule and think there's a double bond there, and you react it with potassium permanganate, KMnO4, and you see a muddy brown color, you've got a double bond. If it stays purple, guess what? You don't have a double bond. It's that easy. How many of you have ever heard the song One-Eyed Purple One-Eyed Purple Man-Eater? I forgot the title. I'm going to have to look it up. But anyways, this is the lab. And let's look at the lab. what you would do is, and I show you how it can be oxidized. Sometimes other forms of a compound, you might see a slight green, but in this one, you never do. You always see that muddy brown. And take a test tube, add a couple of 10 drops of the potassium permanganate solution, which is already made up for you. Add about 5, or I say if you want to have fun, add 10 drops of the alkane or alkene to be tested and mix the test tube. By the way, I didn't show you. We either have electronic mixture, vibro mixers they're called, but I also show students, if this were a test tube, never ever mix the test tube this way. You hold it real firm. If you don't want to use the vibro mixer, they're fun, vibro mixers. It's a plate you push down and it goes like this real fast and mixes it. But if you don't, take test tube, 2 fingers, 1, 2, 3, 4, and really hit it hard like that. Don't tickle it, that won't mix it. And that's how we mix it. And if you did that, you'd see cyclohexane, you observe a purple color, cyclo-1-hexene, muddy brown, and let's again make this 1-octene. You get muddy brown, limonene, muddy brown, unknown A, ooh, they're back again, is muddy brown, and unknown B is purple. And through the miracles of the internet and YouTube, I think everything's on YouTube except my high school graduation. That was too long ago. Now in this one, you gotta go, and I don't have in the lab, to about 52 seconds into the video, but I'm gonna show it to you. Notice here's the potassium permanganate solution. It's purple.
Of potassium manganate 7 oxidizes alkenes to the corresponding diols. Dark purple manganate 7 ions are reduced to insoluble brown.
Hold on, why can't I get rid of this garbage? Nope, that's not what I want. All right.
My job.
Excuse me. Let's try this again.
An alkaline solution of potassium manganate 7 oxidizes alkenes to the corresponding diols. Dark purple manganate 7 ions are reduced to insoluble brown manganese 4 oxide, which produces a turbid brownish suspension.
Well, you got to see the muddy brown.
Here's what happens when you use an addition reaction to identify an alkane from an alkene using bromine.
I forget I have YouTube set up. And in real life, the way we do it, you'll actually see the whole thing coated and going to a muddy brown color if you have a double bond. If not, it stays purple. And if you notice here, I have table 3, and you would actually go in the lab and do these, mix it, and this is what you'd observe. Again, muddy brown or purple. And that will tell you whether that has a double bond or not. Now, if you notice, I have at the end questions. Here I asked you to draw the structures again. I guess you don't really have to put it in table 1 if you don't want to, because I'm asking you to draw it again. And for some of these questions, please use your experimental results to justify your answers. They're not hard. There are 4 of them. And with that, I'm done. And in real life, I'd look at the clock and say, all right, everybody, let's go to the lab. And I'd first show you the demonstration with the bromine, like I just showed you the results. Then you would go smell the different chemicals. And you'd also do the reaction with potassium permanganate with the different chemicals on table 3. And then when you're done, you clean up and leave. And we're done. So with that, because tomorrow's Yom Kippur, I'll use the traditional greeting, Good Yontif, and also the other one, may your name be written in the book of life for next year. And one thing, between sundown tonight and sundown tomorrow, Thursday, I will not be answering. I won't even be checking my emails. But after that, I'll be on my regular schedule. Don't forget, I have an office hour tonight. If you have any problems or questions, stop by. And also, don't forget, Monday, I'll go through the aromatic problem set. I'll also do my world famous review for next test, test number 1. And with that, gang gesund. Have a nice rest of the week and weekend. I'll see you on Monday. Don't forget, a week from today will be test number 1. Bye, gang gesund.
Thank you.